it turns out the other day I was just Googling around and I came across some images for Shor's algorithm. And I kind of I was a bit surprised to see that uh, it kind of it kind of seems like this is the same circuit as phase estimation. So I thought maybe because phase estimation seems pretty abstract so far. Yeah, I mean it seems like this is this, right? That's just the inverse of the quantum Fourier transform. Okay, here they do this, but they call it like a x to the power of a. Mm, yeah, but it seems like that is the. I mean, that is definitely the picture that you see here, right? And that is phase estimation. So maybe Shor's algorithm is just a. I mean, maybe I should. I can, because the phase estimation is pretty abstract in and of itself in terms of what it does. So it seems to be that at least the last time it seemed like this. Didn't really understand. I understand how this is structured, but like not really what is the purpose of doing this. And maybe because here it's like I mentioned above, circuit estimates the phase of a unitary operator u. It estimates theta in this whatever, but like why is that relevant, right? And maybe it's one of those things where um, if I try to approach that from Shor's algorithm perspective, then maybe I will understand this better, because it seems like Shor's algorithm is phase estimation. Um, that's what it seems like, and maybe just as a way to rephrase the problem, right? So, and maybe that's another reason why Shor's algorithm doesn't have a specific page in the IBM-Q experience. Let me think. How can I? So Shor's algorithm. Uh, maybe we can watch a video. No, or maybe. Um, Factorization. All those seem to be rather lecture stuff, which is probably going to be complicated. Maybe let me just check these. I don't know. I'm just clicking randomly. Yeah, Jonathan Hui. I've read some. I think I was scanning some of his articles, and they were pretty good. Um, so maybe I should start here, and then okay, I see here some of those mod things, and then maybe that's the way that this is translated. Oh, I see. Look, repeating. It repeats. Oh, I think I know what's. So it's probably okay. So this is probably something that it's kind of okay. A way to rephrase the problem so that then you can find what's that repeating pattern, and that's why you use the inverse quantum Fourier transform, and then this is gonna somehow tell you or help you to the factorization. Probably not in the quantum processor, but outside of it. So let's just take a look at this. Let's just take a look at these people. Maybe that's gonna help. RSA, blah blah blah. It's based on simple idea, prime factorization. Okay, we're not interested in that, but I mean that's the idea, right? So you've got this integer and those are prime numbers. Based on this symmetry and complexity, we can distribute publicly based, blah blah blah. So this is also the base, so the business or the industry context of why this problem is relevant. So RSA encryption and stuff like that. RSA algorithm. So the following is the RSA algorithm. You can take our words for now that if we know how to do prime factorization effectively, then RSA will be history. So this is how RSA is done. So generate two large unique prime numbers, P and Q, compute N, select a random number, select a random, generate two large, you can't believe me that I didn't know that. Generate two large prime numbers. Select a random number such that the GCD is probably the like the common the greatest, exactly the common divisor thing. That equals to 1. Okay. compute the unique integer such that e times d equals 1 mod this, and then this is the private key, and then this is the public key. Okay. Represent a message as an integer m. Send out the encrypted message data as this. However, we do need to understand a couple of terms above. GCD finds the largest divisor between two numbers. For example, 3660, it's 12. Okay. Two numbers are co-prime if they don't have any common factors. Okay, so then the GCD is 1. Mod is the modulo operator that programmers familiar with. Okay. So 7 mod 10 is 7, 17 mod 10 is 7, minus 1 is 9. So it's basically, like modulo 10, right? So then once you go over 10, you start over. So, okay, so you've got some operations. 11 which is 1 modulo 10. For example, 7, okay, 7 to the power of 3, 7 to the power of 2 times 7. Okay. These tricks become handy to compute this. Okay, prime factorization complexity. With classical computing, the best way we can solve prime factorization is this. The number of bits, number of gates, about. Okay, Shor's algorithm can do it in this. Okay, prime factorization, that's what we're interested in. But to solve it, we need to formalize a solution in an unusual way. That's what I kind of suspected. Let's find the prime factors for 21 with the equations below. Magically, these equations end with the number 7 and 3, which is our answer. Okay. Wait a second. Why is this starting with 8 to the power 2? 21 divides 8 plus 1 times 8 minus 1, because this is then part of that. Okay. But this is not simple like. There are many mathematical theories behind them. The basic idea is to find a number, 8 in our case, which is with its square equals the term on the right below 1 mod 21. So 21 is the number we're trying to factorize. So you gotta find a number that, if you square it, is equal to 1 modulo 21. Okay. Why? So let me just go back here for a second so I understand this well. So you compute a large number n, which is multiplying the two prime numbers. And then this number, which is basically p minus 1 times q minus 1. Okay. And so you find a number e such that the common divisor between e and this number is 1. So you select 1 and then compute the unique integer d, that d times e equals 1 modulo this number. Okay. dn en. And then the data is encrypted this way. C. Send the message as an integer m in the interval. And then you do m to the power of e mod n. So the decryption is that you got a message, then to the power of d modulo n. So this gives you m. And if you know m, because E is part of the public key and N is part of the public key, then you can decrypt C. So this kind of makes sense. But okay, prime factorization. Where were we? So let's try our luck again. Start with a random guess. X equals 2. First, we want to know whether X and N are co-prime. That can be done with the Euclid's algorithm. So there's an example to find the common factor between 21 and 15. 21, 15. So 21 is 15 times 1 plus 6. Then 15 equals, okay, then this. So 15 is here, and then, so this is 6 times 2 plus 3. That's already an answer. Back one step. Okay. So once you get to 0, then you're back one step. So 3 is the common factor between 21 and 15, and therefore 21 and 15 are not co-prime. If X and 21 are not co-prime, GCD of between X and 21 will be one of the prime factors, and we're done. But don't expect it to happen frequently in a real problem. Most likely X is a co-prime with N. Now we compute the following series of power functions with X2. 2 to the power 0, power 1, power 2, power 3, power 4, power 5, power 6. So it repeats. This function has a period of 6 because if it's 2 to the power 6, it repeats 1 modulo 21. The function values repeat itself every other 6 values. If r is divided by 2, it becomes 3. The number 8 we want is simply the 2 to the power 3. I feel it's going a bit too fast, but I think that's for me. But I think that's a good. I feel that's going to be the sort of the key to understand that. So in summary, we start with a guess on X and verify whether it is a co-prime with N. If not, we use GCD to find the prime factors. Otherwise, we compute the period of the power function. If the period r is even, the number we're speaking is x to the power of r divided by 2, the one underlined in red below. If r is not even, then we take another guess on x and try again. In practice, you should have a pretty even chance of getting the period to be even. Consider the case for n equals 15. We have this. So many choices of x will lead us to the right solution. The odds are pretty favorable. The difficult part is finding the period of the modulo function. Shor's algorithm leads us to a class of algorithms called bounded error probabilistic polynomial time, BPP. In complex theory, we calculate the complexity of the worst case scenario, say ON. In practice, there are problems of finding the solution in polynomial time is the common norm, even though the worst case scenario is still exponential, but the chance is usually extreme small. Unfortunately, finding the period of the modulo function above cannot be solved easily by classical computing. That is where quantum computing comes in. Once the period of the following function is found by quantum computing and is even, we compute the GCD. So that's the idea. Okay, so I haven't fully grasped, but I'll probably do another run on this, but I haven't fully grasped, but that's what I mean. So basically, they reduce the problem in a way that it can be solved by finding the period of that function. So when is this function repeating? And that's why the phase estimation comes in handy. Okay, it's bound by quantum computing and it is even. We compute GC. This is easily done with Euclid's algorithm, as we discussed before. But to understand the period finding method, we need to cover a few basic concepts first. Okay, but a quantum Fourier transform. Yeah, but I wanted to know. So okay, so I get what I'm getting at is that this function here this function here, it's kind of what you're trying to encode with this part of the algorithm, I guess. Because what you're trying to do intuitively, what you're trying to do intuitively is you're trying to get that nice picture of like, so you're trying to, what you want to do is, let me show you maybe here. So you want to have that, wow, this is really nice. So you probably want to have, my guess is you want to have each of those things in a superposition, right? And so then the inverse of the quantum Fourier tells you, okay, so your period is 6. Because the quantum Fourier transform, yeah or not? Because the quantum Fourier transforms give you the frequency, but the inverse will give you the period in this case. It feels correct, but I'm not so sure. So you want that. I'm a bit confused because it seems like that would be the input you would normally have to then apply the quantum Fourier transform and actually get that 6. So I don't know why is the inverse used in this case. Can we clear this out? I don't know. Okay. So, but this we know, QFT we know, QFT we know, QFT we know. But this seems like a good explanation as well, by the way. QFT we know. Phase estimation, that's where I wanted to get at. Okay. So, oh, perfect, nice. That looks like it looks like this is gonna really help me. Perfect. Definitely check this. Definitely check Jonathan's articles. They seem super well explained. I'm gonna leave this video here. So basically, so my suspicion was correct, which is basically this is about Shor's algorithm being phrased in a way that then phase estimation becomes solving the algorithm. But it seems like you're going to have to run that phase estimation many times until you find what you want to find. But this is the gist of the idea. So okay, so that's pretty nice actually. So it's just okay. So it's expressing it using this modular thing. So and again, it's a pretty neat example of how basically the structure of the problem is helping you solve it with a quantum computer. Cool. So what I'll do in the next video is I'll go through the phase estimation article, and then maybe I'll kind of recap a little bit the basics here. I'm not feeling super confident that I kind of fully grasped it, but at intuition level, it feels good. It feels good, right? So as I said, it's about phrasing it in that form where the problem then is reduced in just finding when does this function repeat, because then you can find the number, which is this 8. Which is this 8. Exactly, this is this 8. Because then you do 8 plus 1, 8 minus 1, and then you so once you have the 8, then you do the GCD of 8 plus 1, 8 minus 1, and then you actually get the answers. So this is, and you do that not in the quantum computer, but you do that in a classical computer. Okay. Okay, so if you are able to find that 8, that's how you do it. And you do it basically by saying, okay, so this is 6, so, and then that's your 8. Okay, I'll go through that again. Don't worry. I'll go through that again because I want to make sure that I really get it. And then the phase estimation, this seems to be especially because it touches also the eigenvalue and eigenvectors concept, which I'm not super familiar with. So I'm going to be really glad to go through that as well. Cool. Thanks for listening, and stay tuned for more.